So the last thing we have to learn for antiderivatives is how to undo quotient rule. And to do this, we need a concept called partial fractions. And what partial fractions are going to do is use algebra to take a rational expression and break it into the sum of simpler expressions. And to do this, the first thing we need to do is we need to factor a denominator. So the numerator is fine however it's written, but we want to factor the denominator. So if I use this rational expression, that would be the equivalent of x minus 13 over 2x minus 1 times x minus 3. And the idea of this is by factoring the denominator, we're going to be able to say that this is going to be the sum of fractions where each fraction has one of the factors as a denominator. So since 2x minus 1 is a factor, that's going to be the denominator for one fraction. X minus 3 is a factor, it will be the denominator for a different fraction. If I had three factors in the denominator, there'd be a third fraction, and so on. The issue, though, is we have no idea what the numerators for these simpler fractions will be, so we just tend to use capital letters. So I'm going to use A and B to represent whatever these numerators are. Next, it's tough to deal with this as it's written as a fraction. So if you've noticed, I've written this as an equation, and to get rid of the fractions, I can multiply my entire equation by a common denominator, which just happens to be the 2x minus 1 times x minus 3. And this way, we'll be able to work with this in polynomial form rather than rational equation form. So when I multiply by a common denominator, I'm going to be left with the x minus 13, because the whole denominator cancels out. For this fraction, the 2x minus 1s will cancel, and I'll have a times x minus 3. For the third fraction, the x minus 3's cancel, and I'll have b times 2x minus 1. So now we have it as a polynomial we can work with, but we still don't know what a and b are. So the next thing we need is we need to know what makes this common denominator 0. Well, looking at this, I would get a 0 in the denominator if x equals 1/2. I would get 0 in the denominator if x equals 3. And the reason we want this is we're going to actually plug each of these in for x and see what happens. So if x equals 1/2, and I plug that in for x in my polynomial equation here, well, 1/2 minus 13 is negative 25/2. Then a times negative 5/2. But then when I plug the 1/2 in here, this becomes 0 and the b is actually gone. And we're left with a simple equation that we can solve for a, and we get that a is 5. If I then go and plug 3 in for x, well, 3 minus 13 is negative 10. 3 minus 3 is 0, so the a is gone, and that's going to equal 5b. And then solving that for b, I get b is negative 2. So by doing this, I now know a and b, so I can now say that this rational expression is exactly the same. So this is the same thing as saying 5 over 2x minus 1 plus negative 2 over x minus 3. These are equivalent expressions. This is just simpler to deal with. So where this gets used is, let's say I wanted to do the integral or find the antiderivative of this rational. I would still approach it as, first, can I just do this kind of like power rule backwards, or is it one that I recognize, which I don't. I would then try u substitution. U substitution, really the only thing u could be is the denominator, and that would mean du dx would be 4x minus 7, and I don't see any way that's going to cancel, so u substitution doesn't work. I would then check for quotient rule, and the way I check quotient rule is, do I see a quotient? Well, yeah, here's a quotient. So quotient rule is a possibility. So I'm going to need to use partial fractions to make this easier to work with. Now please note the little note I had at the top here. Partial fractions only works if the degree of the numerator is smaller. So degree on top is 1, degree on bottom is 2. Partial fractions work. And we already did this partial fraction. So this is going to be the same as the integral of 5 over 2x minus 1 plus negative 2 over x minus 3 dx. And oops, what we can do here then is we can split this up into two integrals because we have our properties, and the sum and difference property for integrals says I can split this up. And so this would be the integral of 5 over 2x minus 1 dx plus the integral of negative 2 over x minus 3 dx. And now these are easier integrals for us to work with. So if I do this first integral, again, I start, do I happen to know what it is off the top of my head, or I can tell it what it is easily? No. I then think, well, what about u substitution? Well, if I say u is 2x minus 1, then du dx would be 2, and dx would be 1/2 du. And so I would have the integral of 5 over u times 1/2 du. That's a good substitution. And I'll come back to the second integral after I finish the first one here. So pulling 5 over 2 out, I would have the integral of 1 over u, and that's natural log of the absolute value of u, which would be 5/2 times the natural log of the absolute value of 2x minus 1. If I now go over to the other integral, again, I start with, can I see what it is easily? No. What about a u substitution? I think that's going to be promising. However, I can't use u because I already used u for the first integral. So I'm just going to pick some other variable to call, and I'm going to use w. So if w is x minus 3, then dw dx would be 1, and dx would be the same as dw. So this would give me the integral of negative 2 over w dw. And I can pull the negative 2 out. I'd have the integral of 1 over w, which is the natural log of the absolute value of w. And I'm done doing integrals, so I do need to put a plus c here because they're all indefinite. So replacing my w, and this is our antiderivative for that initial integral.